All right, so to continue, college algebra, exponential functions. So there can be various exponential functions. They can be exponential growth, exponential decay, and that depends on the base maybe and a little bit about the exponent. But here's something. There's one really famous number, famous base, and it's this number called e. So this may be new to many of you. E is a very famous number in nature. It's 2.71828, blah, 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 blah. It's kind of like pi. Pi is a famous number in nature that has a decimal representation that goes on forever. We refer to it with the Greek letter pi. This is another famous number in nature, 2.718, that we refer to with this number e, this letter e, but it's just a number. Now we use it as the base of an exponential function. And when we do, we call it the exponential function. So here's the exponential function. Now it's 2.7 to the x, so that's good old exponential growth. If you plotted points, you could plug in a 0. What's e to the 0? Just like anything to the 0, it's a 1. And I said it's because it's bigger than 1, this is exponential growth. And so it looks like this. It approaches this asymptote here. You know, it's kind of like a 3. Sometimes I just roughly think of it as a 3 to the x. 3 to the x would be just slightly steeper. 10 to the x would be slightly steeper. 2 to the x would be slightly less steep. But it's a very famous number, and it's just an exponential function. Now, let's just step this up a notch. You know, what if I have this guy? All right, that's just an exponential function. Now, the base is the number e. The exponent is on the base e. That 4 is not part of the base. That 4 is waiting out front. And so now, what just happened is you've multiplied a function by 4. And we learned that multiplying by a number vertically stretches that number. So this picture gets vertically stretched, which is kind of hard to do. Let's just say this. When you plug in a 0, what do you get? When you plug in a 0, you get e to the 0, which is 1, of course, but then 1 times 4 is 4. So yes, it got stretched, but we have this new y-intercept of 4. So our graph looks different. It looks different. It wasn't a shift up. That was not a shift up. That was a stretch up. But to me, what happened is this number in front is the y-intercept. So let's try another one. What about f of x equals 6e to the negative x minus 10? All right, now we're getting somewhere. Okay, this is getting a little more complicated. What do you think the minus 10 does on the end, out on the end of the function? Well, we've learned that. Subtract 10 on the end of any shape function, it shifts it down 10. You know, so if I had this function and shifted it down 10, except it's not exact, I switched it up, sorry. I would shift the whole thing down 10. That means the asymptote shifts, the graph shifts, the y-intercept shifts. You know, that might be a good way to approach this problem. For just a second. So the base is e, no big deal. 2.7 is just a number. You could plot points. You should have an E button on your calculator. I'll talk about that in a minute. But I'm trying to graph some fancy graphs here. Let me think here. You know, let's just forget about the shift down 10. This is a shift down 10. Let's forget about that just for a second. Cover it up. Plug in a 0. What do you get when you plug in a 0? E to the 0 is 1 times 6. We just got a 6. I plugged in a 0 and I got 6. Hey, I was about to draw exponential growth, but wait a minute. We learned that if that negative sign is on the x, that's not growth, that's exponential decay. So this is a picture of exponential decay, decaying toward the x-axis like that. All right, that's a picture of this function until, oops, I forgot to shift it down 10. When you take this function and shift it down 10, now that asymptote that was at y equals 0 gets shifted down 10. So where is it now? from 0 down, it's down here at y equals -10. That's the new asymptote. It got shifted down 10. What about this 6? It got shifted down 10. That y-intercept got shifted down 10. So it's at -4. There's the y-intercept. And this whole graph gets shifted, so it's this picture. So I'm thinking about that y-intercept by shifting down 10, thinking about this y-intercept and then subtracting 10. But watch this. If you plug in a 0, e to the 0 is 1, times 6 is 6, subtract 10 is -4. So you can get that. I like to ask these questions. The book doesn't exactly ask these questions the way I do. I like to ask these questions. I like to ask, what is that horizontal asymptote? Horizontal asymptote. And it's this kind of this imaginary line here. It's this dashed line, and it's y equals -10. That's its name. It's not a point. Please don't give me a point. It's a line, y equals -10. So that's the asymptote. Let's see, I might ask, what's the y-intercept? And we just found the y-intercept. When you plug in a 0, you can do the math. You can do the math. When you plug in a 0, you get -4. We just did that. Hey, I might ask for the x-intercept. I've asked for it before on these exponential functions, and there wasn't an x-intercept because it never touched the x-axis. But since this one got shifted down 10, look, there is an x-intercept. So how do you always find an x-intercept? You let y equals 0. Let's go right up here to try to find the x-intercept. We're going to let y equals 0. Sorry, I circled this. We're going to let y equals 0, and we're going to try to solve this exponential equation. Now, that means we have to solve for x. So I got to teach you something new. I got to teach you how to undo the e to the x. I got to teach you about the inverse of e to the x. That's okay. First, we can add 10. Add 10 over here. Divide by 6. Divide by 6. But now I got to get the x out of the exponent of this e function, and I want to undo the e function, and that's where the inverse of an e function comes up, and it's a logarithm. So I haven't taught you about logarithms. It comes up in the next section, but what I'm teaching you now is where to use logarithms. You use it to help you solve an exponential equation. So what I do is I take the logarithm of both sides. Now this particular there's a lot of different logarithms. I'm going to do the natural logarithm. So it's called ln. That's an ln of 10/6. I'm not multiplying by ln. It's almost like square rooting both sides or squaring both sides. I'm logging both sides. Natural logging the 10/6. And when I natural log the e to the -x, these two guys are inverses of each other. They cancel each other out, and we just get a nice -x equals the natural log of 10/6. Oh man, you are close. You got one more step in order to get x. Multiply by a negative or divide by a negative. X is the negative natural log of 10/6. You could pick up a calculator and try to find your natural log button. And it should be next to your E button. I'm going to try this. The natural log of 10 divided by 6 is 0.5108, and it's negative 0.511. I'm going to round it to 3 decimals. That's my x-intercept. There it is. That's awesome. I'm going to go over here and put it. You know what I'm going to put over here? Negative natural log of 10/6, comma 0. That's the x-intercept, or approximately negative 0.511, comma 0. I got more to teach you about logarithms, but I thought it was smart to just tell you where they're used. They're used to undo the exponential function. All right, more to say here in 5.2. I'm going to hit pause here.